Hello and welcome to today's lesson where we're going to look at momentum in the GCSE separate science physics topic of forces. So in today's lesson we're going to try and define and calculate momentum. Now if we learn and we are successful in today's lesson, we can define what we mean by the quantity momentum, we can calculate momentum from information, and we can apply this information to understand how momentum can be used accurately and reliably in different contexts. So we're going to look at the following part of the AQA separate science physics specification in forces for momentum. So we're going to look at 4.5.7.1, momentum is a property of moving objects. So over 300 years ago, Isaac Newton put forward his ideas on how objects move. Now Isaac Newton spent most of his life looking at how everyday objects interact with each other, and he called these ideas the laws of motion. And to this day we can still predict the behaviour of objects on the everyday scale of the universe using only Newton's laws of motion. So objects like cars or rockets or humans, they can be extrapolated and understood using Newton's laws of motion. So Newton's laws of motion are an excellent understanding of everyday motion in the universe. Now as you'll look at if you decide to do A-level physics, that Newton's laws of motion don't apply to motion inside of an atom. Here we use quantum mechanics instead of traditional mechanics. Now just to clarify, Newton's laws of motion are not wrong, rather they're incomplete. They just don't work on this small scale. Now in addition to that, when we look at relativity in A-level physics, once again Newton's laws of motion do not apply to motions inside very strong gravitational fields or speeds approaching the speed of light, so we came up with a theory of relativity. So again, it's not that Newton's laws are wrong, they're just incomplete. Now in fact, if you simplify the theory of relativity and weak gravity and slow speeds, you can actually pull out Newton's laws of motion. Now in the modern day, Newton's laws of motion are commonly stated as Newton's first law, the law of inertia. Objects stay at rest or move with a constant velocity unless acted upon by a resultant force. Newton's second law, resultant force equals inertial mass times by acceleration. And finally, Newton's third law, when two objects interact, they exert equal but opposite forces of the same type on each other. However, when Newton wrote these laws down, he did not write them down in the format that we use today. In his book, the Principia Mathematica, he wrote them in terms of a quantity he invented, momentum. Now, momentum is how difficult it is for an object to change its motion. So if it's difficult for an object to change its motion, it has a high momentum. If it's easy for an object to change its motion, it has a low momentum. So momentum and inertia are very closely linked to each other. Now, inertia describes an object's resistance to change in motion or lack of motion, and momentum describes how much motion it has. So momentum is your force or speed of movement, but inertia is what keeps you going. Now, momentum represents the amount of motion an object has, and it can also be considered a measure of the kinetic energy of an object, whilst inertia is a characteristic of an object that resists change to its state of motion. Objects which are harder to move or whose motion is harder to change have more inertia. So for example, let's look at this particular concept. A running rugby player has a high momentum. A moving bus or a truck has a high momentum. Now what qualities do they possess to have a high momentum? What makes it difficult to change their motion? Well, it's their masses and their velocities. Both those objects have relatively high masses and high velocities, so it gives them a high momentum. So momentum of an object is dependent on two factors of the object, the mass of the object and the velocity of the object. And we can express this in the form of an equation. Momentum is the mass in kilograms times by the velocity in meters per second. Now this is why momentum is similar to kinetic energy. It contains the same terms. So whilst momentum is mass times velocity, kinetic energy is a half times by mass times by velocity squared. So you'll see they'll be very closely linked to each other because they are varied by the same factors. Now you are expected to recall and memorize this equation for your examination, and you can even use this equation as the definition of momentum. So if an examination says to you define momentum, it's perfectly legitimate to write down the equation to do so. Now we can symbolize this equation with the symbols P equals mv. Now momentum is given the symbol P as it's the first letter of the Latin translation of momentum, or another word that Newton used, impetus. Now Newton realised that a resultant force was needed to change the velocity of an object, but he also realised that the effect of this resultant force depended on the object's mass. Now in the modern day we know this as F equals ma, Newton's second law of motion. Now just to clarify here, it's better to term mass as the inertial mass here, because remember that's the measure of how difficult it is to change an object's motion. Now Newton decided to simplify this system to make it easier for people to understand. So he considered the product of inertial mass and the velocity as the momentum of the object. So momentum is a simplification to band two terms together which affect the motion of the object. So this means for objects with the same momentum, the larger the mass of the object, the lower its equivalent velocity, and the smaller its mass, the higher its equivalent velocity. Now we can work out the units of momentum by looking at the equation. So if we notice we're times in mass and velocity with each other, so we have to push the units together. So because mass is in kilograms and velocity is in meters per second, momentum is kilogram meters per second. So we've combined the units of mass and velocity as they're being multiplied in the equation, which we can also express in this format as well legitimately. Now, momentum is a dynamic quantity, which means all moving objects have momentum and all stationary objects not moving do not have momentum. So every object which is in motion will have a non-zero momentum. Now the reason for why this is momentum equals mass times by velocity. So if velocity is a non-zero number, you will get a value out which is non-zero, but if velocity is 0, you will get a 0 momentum out. So that's very important to remember. Now momentum is a vector quantity because it contains velocity in its equation, which is a vector. So the direction of the vector, the direction of the momentum, is shown by the sign of the calculated value, plus and minus. So objects moving in opposite directions will have opposite signs. So you can change the momentum by either altering the speed or the direction of the object, which is a very common question. So if an object is bounced off a wall, it will still change momentum because it's going from a plus value to a minus value, or vice versa. Now, unless stated in the question, you can assign the plus and the minus with the direction you choose to. So let's just recap what we've learned. Newton defined momentum to be mass times by velocity and defined the unit to be kilogram meters per second. Now momentum is given a symbol of P and it's a dynamic quantity. So it can be calculated with the following equation. Momentum in kilogram meters per second equals mass in kilograms times by velocity in meters per second. And momentum has both a magnitude and a direction. It's a vector quantity. And if objects are moving in opposite directions, they have opposite momentums, so signified by one value being a positive and the other value being a negative. Now this allowed Newton to write his laws of motion in terms of momentum. So he wrote Newton's first law, which we know today as an object will stay at rest or will move with the constant velocity unless acted upon by a resultant force, as a resultant force changes the momentum of an object, which will be important for later in the course. Newton's second law, resultant force equals inertial mass times by acceleration, can also be written as a resultant force is proportional to the change in momentum every second. And Newton's third law, which is when two objects interact, they exert equal and opposite forces of the same type on each other, can also be stated as, for a system of objects, the total momentum of the system before equals the total momentum of the system after, as long as there are no external forces on the system. Now, when Newton wrote his laws of motion in 1687, he published his work in his book, De Principia Mathematica, the mathematical principles of natural philosophy, which is the name for physics back in those days. Now, in this book, Newton wrote his laws of motion in terms of momentum, not in terms of forces. So momentum is the true quantity Newton used to describe motion. Now, there are only 400 copies of the first edition of the Principia Mathematica, which were all signed by Newton, and the first edition is valued today at about £3.7 million. Now, the Cambridge University Library has Newton's own copy of the first edition of the Principia Mathematica with his handwritten notes for the second edition, and this is actually currently thought to be the most valuable book in the world. Now, as we said before, Newton's third law of motion, which is the idea that the total momentum before an event equals the total momentum after an event, is one of the most important laws of physics, and we'll spend an entire lesson looking at that particular principle. Now, this basically states that momentum has to be conserved, has to stay the same for a total system in any collision or explosion. So the total momentum before equals the total momentum after. So the mass times the velocity of the objects before equals the mass times the velocity of the objects afterwards. So whilst the momentum can change between objects, which requires a resultant force, like Newton's first law stated, the total momentum of all the objects has to remain fixed. So that is the conservation of momentum, and we'll cover this more in upcoming lessons. Now, this can be shown in many different examples in physics. It governs the mechanics of all collisions and all explosions in the universe. All of these examples are examples of the conservation of momentum. Now, let's look at an example of how to calculate a momentum of an object when considering its motion. So we can calculate the momentum of any object when it's in motion. So, for example, Alan St. Maximin is running with the football at a speed of 8.8 meters per second. He has a mass of 67 kilograms. What is his momentum as he runs? So you write out the equation. Momentum equals mass times velocity. You check your mass is in kilograms and your velocity is in meters per second. You then put them into the equation and you show that before you do a calculation to prove to the examiner you know what the mass is and you know what the velocity is. You then calculate your value and you get 589.6 kilogram meters per second. But then we look at our values and we see there are two significant figures in the question from 8.8 and 67. So we write our answer to two significant figures, 590 kilogram meters per second. Here's another example. Valtteri Bottas is driving the French Grand Prix. The total mass of Bottas and the car is 710 kilograms. He's traveling at a velocity of 120 meters per second. What is his momentum? So we say momentum equals mass times velocity, and we go 710 times by 120, so we get 85,200 kilogram meters per second. Now that means he's got a lot more momentum than Alan St. Maximin from the previous example, so it's a lot harder. You need a lot bigger resultant force to change this particular motion of this particular car, which makes sense because it's easier to stop a human than it is to stop a car. Now, just to clarify, in our question, have we given it to the correct units? Yes, we have. Have we given it to the correct numbers of figures? Yes, we have. So the answer will be correct. Now, in this lesson, what have we learned? Momentum is defined by the equation. Momentum equals mass times velocity. And you should be able to use this equation, recall this equation, and apply this equation. Now, if you've been successful and learned in this lesson, you should be able to define what we mean by momentum, calculate momentum from information, and apply this information to understand how momentum can be used to accurately and reliably calculate different values in different contexts. I hope you've enjoyed this lesson looking at momentum, and have a lovely day.